So next up, my colleague George Wilson is going to be talking about compressed ARC as well as kind of the ARC more generally and a bunch of improvements that he's made. So thanks.
Thanks, Matt. So one of the things that I wanted to do was go through and kind of talk a little bit about the ARC, so as well as some of the changes that we've recently made. So the first thing that I'm going to do is talk about, kind of give everybody an overview on the ARC and kind of some of the terminology that is used within the ARC. So it'll make more sense when I start talking about the compressed ARC design. And then we'll go into compressed ARC, and then I'll talk a little bit about how it's going to integrate or has integrated with the L2 ARC and kind of the changes that it has made to simplify things. And then finally, I'll talk a little bit about the performance enhancements that we did on top of the compressed ARC, and I'll go into more detail on why that was necessary. So first, I'll start with just kind of describing a little bit about the ARC. ARC stands for Adaptive Replacement Cache. It is the primary consumer of RAM within ZFS, and by default takes every piece of RAM except for like 1 gig. It's designed to be a scan-resistant file system cache, and it's comprised of 2 separate LRU caches. So it breaks it up into most recently used and most frequently used caches. It has the benefit of being able to adapt to memory pressure. So if there's a big demand from other consumers of kernel memory, then it will actually notify the ARC, or the ARC will detect this and start to shrink down. All the blocks in the ARC are cached uncompressed. So it's just the same logical data that any of the consumers that are trying to do reads, they would simply get that data back. And then the last thing is that these 2 LRUs will actually adapt based on the workload. So if you're having a workload that is accessing data frequently, then the most frequently used cache will actually start to grow and start caching more blocks. The most recently used cache will actually shrink down. So before I go into more details on kind of the inner workings of the ARC, it's probably good to make sure that people understand kind of the terminology. And I'm sure you've heard some of the stuff today from previous talks. So this is kind of the design of what you would see when you're looking at the ARC. It's comprised of a hash table, which uses a triple to actually insert ARC headers into the hash table. Whenever you actually read a block, we use this triple of the SPA GUID, the data virtual address, and the block's birth time as a way to hash into the hash table and insert that ARC header into the hash table. The ARC header itself will actually point to ARC buffers. The ARC buffers are where we store the data, and that's what is actually, whenever you have a block that's cached, it's actually storing the data in the ARC buffer. Other things to note, you'll see things in this presentation like P size and L size, P size, physical size. You can think of that as the actual like compressed size of an object versus L size, the logical size, is kind of the uncompressed version. So if we look at this in a little bit more detail, we see that if you were to look at the hash table, you'd have a bunch of different buckets, and each of them pointing to 1 or more ARC headers if there was something cached in that entry. The ARC headers themselves can actually be chained. So one ARC header can point to a next ARC header if they happen to hash the exact same bucket entry. If you have an entry in the hash, then it is considered a cached block. So we can have ARC headers that are considered to be anonymous, which means that they're not discoverable. They will not live in the hash table. If we then go into more detail on the ARC header and start looking closely at the ARC buffers, we see that the header itself has a size entry. This is the logical size of the cache data that is actually stored with the ARC buffer. It also has the same triple that is used to insert into the hash table, so that information is readily available whenever we have a cached block. And then it has a pointer to a chain of ARC buffers. Now it's kind of interesting to note that typically we have only 1 ARC buffer off an ARC header. And that's what we would really like to see to make sure that the ARC is actually as efficient as possible so that we're not duplicating memory. Because every single time we have additional ARC buffers, we're caching the same data twice. or multiple times. And we actually introduced a small project called Single Copy Arc, which was actually designed to actually remove these extra copies and leave the arc simply with just one copy of the cache data. Just to kind of back up, whenever we actually have multiple copies, this circumstance actually happens whenever you're reading from, say, a snapshot, for example, or clones that are coming off the same snapshot. The reason for this is that every single time that you want to access a block, if that block happens to be shared, it's still pointing to the exact same block on disk. But we optimize for the case that you may want to update that block from two different data sets, for example. So you may have a data set that's, tank A file and tank B file, but they're all coming off the same snapshot. They may eventually update that block independently. We create an arc buffer for each of those data sets to access it. And I'll show you exactly how that happens. It's one of the scenarios that we'll go through. So this is what it looks like when we actually try to read uncached data. So in this case, we're reading a file. We come in through the ZFS read system call. It goes into the arc. The first thing we look at is to see if it actually exists in the hash table. So if it's not in the hash table, we'll come to the I/O pipeline and go and issue a physical read to read it off disk. The I/O pipeline will decompress the data if that data is compressed, and will store the data back into the arc buffer as an uncompressed block. That same data will then be passed back to the consumer, whoever actually requested the data. If we're reading cache data, then again, we would look in the hash table. We would find that it already exists and simply return back that data as a cache hit, again, to the consumer. And again, we're returning back the uncompressed data. And then the last case that is worth talking about is this case where we have multiple arc buffers. So if we go back to this case, we saw that we were reading from tank foo, and here we happen to be reading from a data set called tank bar. If this data set were derived from the same snapshot and was sharing that block, when we actually go and read this data, we would look in the arc header, we would find the same GUID, DVA, and block pointer that we're interested in. So we would find the arc header. We determine that there's already an arc buffer, but it doesn't actually belong to us. So we would make an additional copy of this, and we b-copy the data and create a secondary copy, and that's what we pass back to the consumer. And I'll talk about why this is relevant when we go into compressed arc. So the penalty here, when this happens, is you have to do a b-copy every single time for every additional access that happens. So now let's go into compressed arc. So first, it's probably worth mentioning a little bit about some of the different compression techniques that are out there in the industry. We're not the first to go after a memory compression implementation within a system. As a matter of fact, I have listed different operating systems here that have already done it. Those of you that are running OS X probably have noticed it. If you're running Windows 10, it's actually built in. Linux has multiple implementations of this, but they've all done something kind of different in that they tend to insert their compression mechanism in kind of the paging stack. So as blocks are getting ready to be evicted out or the demand for memory is increasing, they'll then start compressing data that hasn't been used recently, and they compress that out instead of just simply paging it out to swap. Interestingly, Robert and I started looking at kind of something very similar to that for ZFS in 2013 at Hackathon from 2 years ago. We took a similar approach where we wanted to see, could we actually have another stage in our eviction process where we would actually compress the data before evicting it out completely from the cache. I'll let you know now that that's not what we implemented. The other observation that we made, and this started becoming more prominent with the introduction of LZ4 in ZFS, is that decompression speeds tend to be pretty damn fast. So we wanted to see, could we actually leverage that to create a design that made it very flexible and actually simplified things. So this is what we came up with. We definitely are leveraging the fact that decompression is fast. In particular, as LZ4 decompression is extremely fast. So the idea is that we never compress memory, we only decompress it. So this got us out of the path of actually having to worry about at what point or what stage would you have to compress memory back. We simply took the approach that every access of compressed memory was simply a decompress operation, and we would pass back the uncompressed data when you actually requested it. The other approach the other benefit that this gave us is that now blocks in memory matched blocks on disk exactly. So if you're using compression in your pool, whether you're using LZJB, LZ4, whatever you have, the block that it gets compressed and written to disk, the next time you read it will be the exact same block, same size, same checksum, and it will be stored in memory. We also wanted to minimize the number of changes in the eviction code, primarily because the eviction code, for those that have played around in the Arc, is pretty gnarly. So we didn't want to make that more complicated than it needed to be. As a matter of fact, through this project, we've actually simplified it. But the idea is that now blocks that need to be evicted simply get evicted just like they did normally. Uncompressed data that actually exists, we try to discard as quickly as possible, leaving just the compressed data in the cache. Because we're now using the same, because we're matching the block on disk to the block in memory, we can now leverage the block pointer's checksum. So Kirk talked about the block pointer earlier and how we actually have these different words that comprise the checksum. In the past, if we did any kind of checksumming in memory, we used to use a very simple Fletcher 2 checksum algorithm. We only did that for debug builds, or I think L2 arc blocks would always be Fletcher 2. Now we can actually leverage the real checksum. So if you're using a much stronger checksum for your pool, we'll use the exact same checksum within the arc, and it matches exactly. This also allowed us to simplify the L2 arc implementation, and I'll talk a little bit more about that in a few moments. So now let's go back to the same picture and see how things compare. So here we have a compressed arc read. And in this case, we're reading the data, again, not finding it in the hash table, going out to disk, requesting it from the disks themselves, but instead, we're telling the I/O pipeline to not decompress the data. What's being returned back is the compressed data, which is being stored in a new block that's associated with the arc header. I'll go into more detail about this in a second. We then allow the arc itself to actually decompress the data, and it will store it into an arc buffer and pass that uncompressed data back to the consumers. So effectively, we've moved this decompression phase, which used to happen in the I/O pipeline, we've moved it up into the arc, and we're also introducing another block that we maintain as part of the cache. So this is what it looks like now. You'll note that we've actually added now a P size to the header, so we now know the physical size, we know the logical size, and we now have this new data pointer which points to a block that matches the on-disk block. We can still have multiple arc buffers like we did before. The difference now is that we try to aggressively evict these so that what we're left with is actually just the compressed data in the cache. We'll recreate these every single time that somebody tries to read data. So in the end, this is what we want to see when we've finished doing a read. So here's the implementation. We start off, the first thing that we'll do is we'll allocate an arc header if one doesn't exist, so this case happens to be a cache miss. So then we allocate an arc buffer. We request the data, but the data buffer that we're actually passing to the I/O pipeline In the past, we used to pass the data buffer associated with the ARC buffer. Instead, we're passing the data buffer associated with the ARC header. We read the data, we read it compressed. We don't decompress in the I/O pipeline. We instead store that data in the ARC header's data pointer. There's a new decompression phase that's been added to the ARC code. We call that to actually decompress it and then store the uncompressed block in the ARC buffer and pass that to the consumer. Once the consumer has read the data and has released all the holds from it, we simply discard it, leaving just the compressed block in the cache. If we look at a cache hit, again, we start off with the fact that we have an ARC header with just compressed data. We'll allocate a new ARC buff header, a new ARC buffer that we're going to pass back to the consumer. We decompress the data and store that uncompressed data in the ARC buffer and return that back to the caller. Once they've discarded it, we simply remove it from the cache, and we're left with just the cache data in the ARC. Writes, however, are a little bit different. We want to make sure that we can maintain the compressed data in the ARC so that after you've done the write, we have the exact same data that's on disk. The way we achieve this actually is quite interesting because we can use the I/O pipeline callbacks to be able to store this data. So when we come in, we start off with an ARC buffer that already has the changed and modified data. We have the compressed data, which is now stale. So we simply free it, and we're going to reallocate it once we have written the new data, or actually compressed the new data. We then pass the uncompressed data to the I/O pipeline. As part of the I/O pipeline, we'll compress that new data, store it back, and allocate a new ARC buffer, a new ARC header data pointer, store the compressed data in there, and then write it to disk. So this allows us to actually always have the correct compressed data in the cache at all times. So with regards to the L2 ARC integration, I mentioned that it actually simplified quite a few things for us. With the introduction of compressed L2 ARC, one of the things that we had to do was actually go and create a new temporary buffer, compress it, track when that buffer was no longer in use, and figure out when to free it. The advantage now is that we already have that compressed buffer. Now it's hanging off the ARC header. So we don't have to have something dedicated for the L2 ARC's use. We simply say whenever you want to write the block to the L2 ARC, you always just write the ARC header's data pointer. If that block is compressed on disk, it will be compressed on the L2 ARC. If it's not compressed on disk, it won't be compressed on the L2 ARC. The other advantage is that we can use the same checksum. So we no longer have to keep around this very weak Fletcher 2 checksum to determine whether or not the block that's in the L2 ARC is stale. Sorry, even the first 64 bits, that's all we store. Yeah. So it's not even the full checksum, correct. Now we can actually use the block pointer's checksum to validate this information. Because now the block pointer's checksum will be the same for the L2 ARC block that we wrote, as well as it's the same for the checksum of the block on disk that we would want to read. The advantage there, again, is that now the checksum is determined by what you decide to use for your pool and not something that's just simply hard-coded in the ARC. A secondary advantage is that we were able to reduce the footprint of the L2 ARC header because we don't have to keep this extra checksum component in memory. So there's been some work, and I'll talk about that, about how we've been trying to reduce the overhead associated with keeping L2 ARC buffers or L2 ARC metadata in the ARC when you're actually caching a lot of data in the L2 ARC. The exception to this, however, is if you happen to turn off compressed ARC. If you turn off compressed ARC, then we actually have to do some manipulation where we will recompress the block and recalculate the checksum to determine if that block is stale on the L2 ARC or not. We still use the same checksum algorithm that's in the block pointer, though. So on the space savings front, my colleague Chris Williamson actually integrated a change to reduce the metadata to data ratio in Illumos. I think it's been out for quite some time. And that brought it down from almost 3% to 1.5%. With the compressed ARC changes, we actually took this a step further. We were able to reduce this almost to 1% by eliminating that 32-byte checksum and also a 4-byte A size. The A size is no longer needed because the physical size is now stored in the ARC header, in the ARC header. So we always know what the actual size is, the allocated size is on disk. So lastly, we wanted to go through and look at some other performance enhancements that we could do. Because if you may have caught this or not, but now with the implementation of this additional data buffer, we have the ability to actually have duplicate data around for quite some time. So the first thing that we came up with was the shared ARC data component. The advantage here is that if you turn compressed ARC off, then what that tells us is that the data associated with the ARC header and the data that would be in the ARC buffer would always be the same because there's no compression, you haven't enabled compression. So these two components are always identical. We would always be storing uncompressed data in the ARC header, and the ARC buffer always stores uncompressed data. So with that in mind, we could actually share them. This is actually an additional feature that we've added on top of the compressed ARC project to get some performance back where we don't actually have to do the decompression phase if you've disabled the compressed ARC feature. Dan also talked this morning about the compress send receive code. One of the advantages is if this header happens to be compressed, then we may actually have the ability to create a compressed ARC buffer, which is sharing now the header's compressed data. We don't have to do another allocation, and it's this ARC buffer that we pass to the DMU code to do the send. These other ARC buffers that aren't actually doing sharing are still storing data uncompressed. And then the last improvement that we worked on was to introduce this concept of a dbuf cache. Because with the compressed ARC, every memory access requires us to go through the decompression phase to create that uncompressed piece of data that we're going to go back to the consumer. It would be nice if we could actually reduce the CPU impact of having to do that for frequently accessed blocks. We now provide a DMU cache, which is actually controlled by the DMU, and it determines which blocks are frequently used, and every single block that remains in that DMU cache or the dbuf cache remains uncompressed. So by default, it's 100 megabytes, so it's relatively small. It has a dedicated eviction thread, which will evict blocks from the end anytime that we're between the low and high water marks. If that eviction thread can't keep up, we actually supplement the eviction process by utilizing the caller's context so that we ensure that we don't ever get to a situation where we simply have the dbuf cache actually grow unbounded. So the idea here is that any blocks that remain in the dbuf cache would remain uncompressed in the ARC until they age out of the cache. Once they age out of the cache, then the ARC is eligible to actually evict them out. So let's look a little bit at some of the examples. So we actually have this code up and running. We've had the compressed components running for about 4 months now, and the new improvements on performance improvements are relatively new. So this example is actually taken from a running system within Delphix, where the system is actually a 768 gig system. And we can see here, this is, I've simply updated ArcStat to show some of the new case stats that we've introduced. So what we see here is that the ARC size itself hasn't even grown to ARC max. We're currently caching, or the current size of it is 446 gig. but the amount of data that is actually in the ARC is currently 1.2 terabytes. I mentioned this is a max physical memory of 768 gig. This overhead is something new that we've introduced. This is the amount of space that's actually being consumed by the ARC buffers. This is that extra uncompressed data that we would maintain temporarily until we can actually evict it out. So at any given time, we're keeping about 600 meg worth of uncompressed data around that's currently being accessed by somebody that's reading data. The ratio here shows us the percentage of memory to uncompressed data. So we're at 2.75x times the amount of data that we can currently cache. So we're caching 2.7 times the amount of actual RAM that we're using. We can also look at this information from MDB. So MDB now exposes this compressed, uncompressed, and overhead size. The compressed size here is every ARC header's P size value. The uncompressed size is every ARC header's L size value. And again, the overhead size is simply the amount of space consumed by the ARC buffers. And I'm right on time, so I think I can probably take like a couple questions. Yes? Yeah, so if the block is not compressed on disk, what you would see is, in this instance, the compressed size, uncompressed size would be the same. The overhead size would still only show whenever we had an ARC buffer associated with it. So effectively, your compression ratio would be 0, because these two would be the same. Overhead size would then only show you any blocks or any headers that currently had ARC buffers associated with them. And that would just be above and beyond what we would normally cache. So that's the instance where we would do, with the ARC sharing, this would be negligible because we would only be accounting for additional ARC buffers that are for, say, a secondary data set, so like a clone or, yes? There's, so as a matter of fact, Prakash, I think, I don't know if this is upstream. Is it, I don't, there's additional case stats, I think, that were added to account for headers, metadata. It is upstream. So there's already some additional case stats. They're just cut off here that shows that additional information. Yes? Have I measured the effects on ARC hit rate? Artificially, yes, on the ARC hit rate. We're still trying to see like workloads. We've gotten some empirical data that shows that at least for our Delphix workloads, customers are seeing a performance improvement. But again, there's not a lot of conclusive data there that, other than like some simple tests that I ran to see could we actually do caching of much larger sizes and running tests against that. What was the second part of your question? Oh, so latency and throughput. Yes, we actually did quite a bit of measurement on latency and throughput with this. I was going to show you a live demo, but we can't get on the Delphix system, so which is unfortunate. But throughput on running this test, like running just a read workload, shows that we use about 1% of CPU for single-threaded reads. If you're doing it on like an overall large system, we ran a test with 8 vCPUs and 128 threads doing IOs, and we were consuming about 10% more CPU than normal. The latencies themselves for reads, for cached reads, are running at about 200 mics. Yes? So the question is, when we actually have a lot of reads, do we actually have a big inflation in memory? Turns out that doesn't necessarily happen when you're doing a lot of reads. The reads themselves get released rather quickly. So as soon as they release and the reference count goes to 0, we immediately evict that uncompressed component, leaving just the compressed portion around. But that's exactly why we wanted to track this data, this number, to see would we see instances where this would go into like the tens of gigs or consuming, some 30% of the ARC. But we haven't seen that. Yes. Yeah, so if we've reached kind of the capacity of the ARC, what happens at that point in time as far as the eviction stages? It goes through the normal eviction code path. We still will set things like ARC no grow to prevent the ARC from growing beyond once it's reached a certain limit, and then we'll start evicting things out of the ARC that are considered to be evictable. So in this, let's go back here. So like, for example, here, if this had actually reached the ARC max, then of this 1.2 terabytes, we would start evicting headers out, and now the compressed data would be freed. Yes? So the question is, after the write, if we still have the uncompressed write buffer, can we satisfy a read from that? Yes, the answer is yes. As long as the read request comes through before the reference count for that buffer goes to 0, then we keep it around. And it's actually a little bit longer than that, because even though it might go to 0, it'll first go into the debuf cache, and then it has to age out of the debuf cache before we actually evict it out. Yes? Great question. So does this imply that when we do a zfetch that we don't do an uncompressed? That exactly implies that. So if you are doing prefetches that don't have an actual data consumer on the other end, then what you're reading in from the I/O pipeline is the compressed data. You're storing that in the ARC header with compressed data, but there will be no uncompressed ARC buffer associated with it. Yes, I'm sorry. Catch me afterwards and...